All right, so in this second video, we're going to focus on proving two other results that were due to Greenwood and Gleason, specifically the values of the Ramsey numbers R of 3, 4 and R of 4, 4. And so let's go ahead and begin with R of 3, 4. And the claim is that this is equal to 9. Now, much like the case of R of 3, 3, it comes down to showing two things. First, coming up with a single example that shows that 8 is not enough to force either a red triangle or a blue K4. And then we want to prove that for every two coloring of the edges of K9, we're always guaranteed to have one of those two outcomes. So let's go ahead and begin with the first case. Now, I'm going to consider a coloring of K8. And I'm going to actually draw this as two separate graphs. I realized in the last video, my blue and my red don't show up very distinctly on here. But it's also probably a little bit easier just to see what's going on if I separate these into a graph and its complement. So that's one thing to kind of think about. There's an alternate way of defining a Ramsey number. Not only can we define it as using a two coloring of Kn, we can talk about a graph on n vertices and its complement. And so let's take a look at the following coloring of K8. So one way that we can color this, I'm going to use red first, is I'm going to connect every vertex to the vertex that's opposite. And then I'm going to connect it to the two next to the one opposite. So this one will connect to that one and this one. This one will connect to this one and this one. This one will connect here and here. This one will also connect here. This one will also connect here, and that's it. So I've now created a graph on 8 vertices in which every vertex has degree 3. Now observe that there's not a single triangle anywhere in this graph. And you can tell that because, well, if you pick any one vertex, if there is a triangle, then by symmetry, every vertex is going to have to be in some triangle. So if I pick this one, well, there's only 3 edges coming out, and none of the ends of those are connected with one another. So there's not going to be any triangles anywhere in this graph. Now let's consider the complement to this. So you can think of this as the blue edges that correspond in the coloring of K8. So this time, each vertex, well, in a K8, every single vertex is going to have degree 7. I currently have 3 edges drawn to each one, so in my new graph, I should have degree 4 for every vertex. Now, certainly everything is going to be connected going around on the outside. So I'm basically trying to draw the complement to this graph. So instead of connecting it to what's opposite and the two next to them, I connect to all the others. So this one, instead of being connected to this one and these two, will be connected to this one and this one in addition to those two. And I just keep following this trend. So this one will connect here, and it will connect here. This one will also connect here. This one will connect here. This one will connect here, here, and then that's it. So every single vertex now has degree 4. This is the complement to the graph I started with. And observe that there's not a single K4 anywhere in this graph. And again, the way that you can make the argument that there's no K4 here is if there is a K4, by symmetry, every vertex will be contained in a K4. So if I look at this vertex here, if it's contained in a K4, there should be 3 other vertices that I can pick, all of which it's adjacent to, and which those 3 form a triangle. Well, I have this triangle here, I've got that one there, I've got this one here, but I don't have any edges here. I mean, we're really close to getting a K4, but we basically have a K4 minus a single edge. So putting these two together gives us our two coloring of K8 that lacks a red triangle and a blue K4. Therefore, what this implies, this one example, is R of 3, 4 must be greater than 8. So it's greater than or equal to 9. Now, it still remains to be shown that this is also less than or equal to 9. Now, in general, we come up with one example like this. That doesn't always mean that that's the only example, but in a lot of cases, there does turn out to just be one example. As we start looking at some some other results later on in these videos. We'll encounter a few other cases where there's just a single example that can be used to argue your lower bound. Now let's go ahead and prove the upper bound for this one. So if we wish to show that 9 is enough to guarantee that this will happen, then we're going to consider an arbitrary red-blue coloring of K9. And unfortunately, there's not really an easy approach to this one. There's several different cases that we have. And what we're going to do is try and build on the results that we already have. What we did in the last case was we assumed that a certain vertex had a given number of red edges coming out of it, and we looked at their connections. And if any one of them was red, it would form a red triangle. The only other possibility is they were all blue. Now, comparing it to this result that we're trying to prove, instead of getting a blue triangle, we want to get the blue K4. So the first case that we're going to focus on is the case where there exists some edge that has at least 4 red edges coming out of it. So case 1, suppose there exists a vertex U that is incident with at least 4 red edges. And let me go ahead and draw it. In fact, I'm going to call them UA, UB, UC, and UD. So at this point, the argument is exactly the same as what we saw in our last theorem. If AB is red, we have a red triangle. If AC is red, we have a red triangle. And we keep working through all the possible edges we can form with these bottom 4 vertices. If any edge there is red, we get a red triangle. The only other possibility is that they're all blue, and then the subgraph induced by A, B, C, and D must be a blue K4. So if any edge subgraph induced by the set ABCD is red, you obtain a red triangle or a red K3. Otherwise, they're all blue, and then that subgraph is a blue K4. So that takes care of this case. In this case, we know the result is going to be true. Let's take a look at another case. And this next one's going to actually build on our R33 result that we had. So we now know the case that we have a vertex, any vertex, that's incident with at least 4 red edges. That's taken care of. So let's look at case 2. So suppose there exists a vertex V incident with at least 6 edges. So I'm going to go ahead and give them names. Let's call them V, let's use W1, V, W2, work our way down to V, W6. So let me draw this picture. I've got my vertex V, and then 1, 2, 3, 4, 5, 6 W1, W2, 3, 4, 5, and 6. And these are all blue edges this time. Now, for this one, it's a little bit different because it's not enough to just have one of these be blue. If I were to make just this one blue, I have a blue triangle, but I'm trying to force a blue K4, so that's not quite enough. So the key here is to focus on the subgraph that's induced by these 6 vertices. That subgraph is a K6, and all the edges are red and blue interconnecting those 6 vertices. We already know something about what happens whenever we have a red-blue K6. We know that there's either going to be a red triangle or a blue triangle. If there's a red triangle, we're done because we're just trying to argue that there's a red K3. The only other possibility is that there's a blue triangle, but if I draw any blue triangle down here and then I include the vertex V, I get a blue K4 out of it. So that's our argument. So the subgraph induced by W1 through W6 is a red-blue K6. So now we're falling back to our previous result. Since R of 3, 3, we know is 6, there exists a red triangle or a blue triangle. In the former case, where we have the red triangle, we're done. In the latter case, we have a blue triangle, and then if we include the vertex V, we get a blue K4. That takes care of this case. We've argued that anytime we have a vertex V that's incident with at least 6 blue vertices, then we're guaranteed to have either a red triangle or a blue K4. So the last thing we have to do is think about what we've missed. We took care first of the case where some vertex was incident with at least 4 red edges. So if that doesn't occur, then each one is incident with at most 3 red edges. But keep in mind how many edges there are in a copy of K9. Every vertex is incident with exactly 8. So if there's at most 3 reds, that's going to give us at least 5 blues. And so the only cases that we've missed at this point is the very specific case where every single vertex is incident with exactly 3 red edges and 5 blue edges. So let's take care of that one. So case 3, every vertex is incident with exactly 3 red edges and 4 blue edges. 5, I misspoke. 5 blue edges. Now, if we were to focus on the subgraph spanned by the edges in just one of these colors, let's maybe focus on the red subgraph. So if we consider the subgraph spanned by the red edges, it has order 9, and every vertex has degree 3. So the key to finishing this up is to remember what was probably the very first result that you learned in graph theory. Namely, it's impossible to have a graph that has an odd number of odd numbered vertices. Every single graph will always have an even number of odd degree vertices. So the point is, this case never occurs. It can't occur because we can't have an odd number of vertices with odd degree. And that takes care of the proof that R of 3, 4 is 9. Now, the second theorem that I'd like for us to look at in this video is the case of R of 4, 4. This one gets a little bit more complicated, but it's also due to Greenwood and Gleason. What they proved was that R of 4, 4 is 18. Now, hopefully at this point you're starting to see some of the difficulty in coming up with these lower bounds. Even our graph that we used to show the lower bound for R of 3, 4 was much more complicated than the case of K5 that we had used to show for R 3, 3. So I'm going to go ahead and switch to a different screen because I'm going to use Mathematica to get this lower bound. So let's take a look at, so hopefully you can see the screen that I have here. And so I've written a command to create what's called a circulant graph, and I'll talk a little bit more about circulant graphs in a later video. But I'm basically forming a circulant graph on 17 vertices, and I'm using as my generators 1, 2, 4, and 8. And again, later on I'll explain exactly where those come from, but there's some abstract algebra involved in actually coming up with this example. And I'm going to go ahead and create this graph. And so here it is, and I've gone ahead and colored the edges in red. Just looking at that, it's really difficult to tell if there's a red K4 or not. It's completely not obvious that a K4 exists in this. So we're going to use another command that Mathematica has built in called the find clique command. Now a clique is just a subgraph that is complete, and that is the largest or a largest complete subgraph. So for example, if I go ahead and find the clique and it gives me something that has 4 vertices in it, that what that means is that the largest possible complete subgraph that you're going to have has 4 vertices. So let me go ahead and run this one. So I've called this graph G1. Now I'm going to find a largest clique in G1. And it gives me 1, 2, 3. Vertices 1, 2, and 3 form a triangle. And I didn't mention this, but here are the vertices. You can think of them as being numbered 0 through 16 going around. And so if I take vertices 1, 2, and 3, they form a triangle, and there's no K4 in here because this is one of the largest complete subgraphs. Again, you can't check this by hand very easily. Now, I want to look at the complement to this graph. And so here, the second command that I have, I called G2 the complement to the first one, and I went ahead and colored it blue. So here's its complement. Once again, it's really hard to tell by looking at this whether or not there's any K4s. So if I use my find clique command, what do you know? I get 1, 4, 7 forms a triangle, but there's no K4s anywhere in here. So putting these two together, in fact, I can go ahead and show G1, G2. Here's my red-blue coloring of K17 that lacks a monochromatic K4. Again, it's not something you can really do easily by hand. But this example alone tells us that whenever we're looking at R for 4, 17 is not enough. So R for 4 must be bigger than 17. Now to show that it is 18, we'll follow the same approach as before. Let's consider a red-blue coloring of K18. Now, for K18, if we consider any particular vertex, it's going to have degree 17. And then we're taking 17 edges, and we're going to go ahead and put them into 2 compartments, red and blue. So if we apply the pigeonhole principle, once again, we know that one of those compartments must contain at least 9 of the edges. So given a vertex U, by the pigeonhole principle, there exists at least 9 edges incident with you that are the same color. So once again, without loss of generality, I'm going to assume that there's at least 9 red edges. I could back up at the end and repeat all the arguments with blue. I'm just going to use WLOG for without loss of generality. Let's go ahead and assume that UA1, UA2, all the way down to UA9. Now at this point, the argument is exactly the same as what we looked at in case 2 of the R34 proof. Specifically, if I look at the subgraph induced by A1 through A9, well, because since I have 9 vertices and R34 is 9, I'm guaranteed that there's either a red triangle or a blue K4. If there's a red triangle, then including U gives me a red K4. If there's a blue K4, we're done. So since R of 3, 4 equals 9, subgraph induced by A1, A2 down to A9 contains a red K3 or a blue K4. In the former case, including U gives a red K4. In the latter case, we're done. And that completes the proof of that one. So you can start to see how we're able to use some of these previous results to build, but there's certainly a limitation on this. And we'll talk more about this in the next video, taking some time to go over exactly what Ramsey numbers are known, which ones aren't, and how we can begin to generalize some of these different ideas. It's unfortunate, but there's only about 10 known Ramsey numbers. I'll give you a complete list in the next video. But there is one that you can use these exact same methods for, and I encourage you to try and prove this one yourself. And again, this is also due to Greenwood and Gleason. So I'm going to leave you with an exercise. Prove that R of 3, 5 is 14. Now, again, there's two separate parts to this. You want to first try and come up with an example of a graph 113 vertices that does not contain a red triangle or a blue K5. That's a little bit harder to do. But the main part is try and show the upper bound. See if you can argue that every single coloring of K14 using red and blue is guaranteed to have one of these two monochromatic subgraphs.